Good evening, and thank you for having me for this talk. We are going to talk about a conservative approach for online credit scoring. So we know that the credit scoring involves the use of analytic methods to transform relevant data into numeric measures that inform and determine credit decisions. In recent years, the use of credit scoring tools has expanded beyond the origin purpose of assessing credit risk, such as establishing the initial and ongoing credit limits available to borrowers, assessing the risk-adjusted profitability of account relationships, and also assisting in a range of loan servicing activities, including fraud detection, delinquency intervention, and loss mitigation. So the critical role for the lending market in causing the latest global financial crisis has increased academic research, policy interest, and bank regulation in this area. And the banking regulatory framework changes brought by the revised Basel Committee on Banking Supervision Accords, later adopted by national legislation in many countries and regions, for instance, the Euro Capital Requirement Directive and the US regulatory capital rules. They introduced stronger risk management requirements for banks with capital requirements tightly coupled to estimated credit portfolio losses. So the recently adopted IFRS 9 and FASB's current expected credit loss, CECL, the different standards introduce revised expected credit loss or impairment calculation rules requiring financial institutions to calculate the expected loss for the banking book over the entire life of the exposures, conditional or macroeconomic factors on a point-in-time basis, that is, recalibrating PDs where necessary to reflect the effect of the current economic conditions. So encouraged by regulators, banks devoted significant resources to develop an internal rating basis approach, okay, the IRB, for the calculation of risk-weighted assets for credit risk to better support decision when granting loans, okay. They wanted to quantify expected credit losses and to assign the mandatory economic capital. So to assess credit risk in developed markets, lenders typically consider historical loan applications and loan performance data collected regularly from a small number of sources on the basis on longest standing banking and credit relationship to develop credit scoring models to evaluate the ability to repay. The willingness to repay also is important, and identify fraud also is important. So we know that the Edward Almanton Z score model for bankruptcy prediction, and also the famous FICO score, the FICO, for retail credit scoring, and they are the oldest industry standards which loan providers still use because of their high interpretability. And these methods are less effective in emerging economies and among low-income unbanked segments of population. This part of the population often do not have access to formal financing or do not earn regular labor income. To cope with these constraints and to improve credit risk assessment, banks and loan providers are increasingly using non-traditional data sets, okay, such as mobile operators and mobile data, utilities, retailers, and so on and so forth. So they want to sophisticate their credit bureaus and credit rating services. This factor poses different sources, and its volume is several times that the traditional sources. So by pursuing this approach, lenders seek to have more accurate information and incentive to grow the credit market under a robust credit control framework. By increasing their use of these new data sources, they try to provide more lending to their public customers and get to analyze loan requests better, ultimately increasing the loan ratio and decreasing the decision time. And people will then have more monthly disposable money for spending, which will contribute to the economy, but it can also create risk for financial institutions. So, as shown in this figure, non-traditional data sets provide the credit market a chance to manage different data sources to boost credit analysis outcomes and follow the stipulated recommendations of standards appropriately. So while this approach presents some opportunities, it also carries some challenges, which are represented in this figure. So first, most of the mobile phone features are redundant and do not contribute to representing credit risk. Second, banks and loan providers should follow the regulators, and the critical changes factor in banking is regulation. So they are regulation-based institutions. It means that fluctuations in the economy and regulations could change the behavior of both banks and customers. Non-traditional data sets can reveal these fluctuations, but current methods are computationally expensive with a high false negative rate. Okay, so the third risk factor is the smart behavior of fraudsters, and it means conscious changes may exist in non-traditional data, which influence the contribution level of features in credit scoring. However, the current methods are not wise enough to renew credit scores over time. As a result, we need highly effective and computationally less expensive solutions to calculate an informative credit score for satisfying the accuracy expectation of financial institutions. Although there are a large number of techniques employed in the development of credit scoring, empirical studies show that the false negative rate obtained is stalled and it's not good enough for non-traditional data sets. So we introduced a novel time-dependent credit scoring method to identify good loans with a low false negative rate. The method uses a two-step approach based on an initial Kruskal-Wallis non-parametric statistic analysis to form a computationally efficient credit scoring model based on an artificial neural network, logistic regression with ridge penalty, random forest, and support vector meshing, SVM, to learn the model and to assess model performance. The Kruskal-Wallis statistic is used for selecting the most prominent features for assessing loan default in credit risk management over time. And this statistic is sensitive to events that are far from the credit scores of good clients, computationally less expensive, and very simple to implement. Additionally, we introduced a credit scoring index that uses the Kruskal-Wallis statistic as a way of feature to decrease the false negative rate, which is able to purify features and decrease the dimensions in real time. This new credit scoring index may be particularly interesting for loan providers assessing loan applications from individuals without any credit history, and based exclusively on non-traditional data analysis. And illustrative empirical results on the use of this novel time-dependent credit scoring method are provided considering a simple credit data set. The empirical finding here show that the new credit scoring methodology represents a reasonable coefficient of determination and a low false negative rate. That is good. And the accuracy is high, and the model is computationally less expensive. That is very important. This is the first study that develops a non-parametric credit scoring system, and it is able to reselect effective features for continued credit evaluation and weight them out by their level of contribution with a good diagnostic ability. So mainly in the literature review of the paper, we talked about credit scoring models using traditional data set, imbalanced learning, and also a comprehensive review on non-traditional data sets for credit scoring with a graphical summary of big data, parallel computing, and MapReduce and Spark that might be interesting for the readers. These are available in the paper if someone is interested. So let us define the null hypothesis that a feature does not contain discriminative information to detect default probability in loan requests. Otherwise, it is an informative feature and will be selected for contributing in the credit scoring. An assumption for this test is that the sample from the credit scores of good clients and credit scores of new clients are independent random samples from continuous distributions. In addition, we consider the time as an index of weights in our credit score method to ensure that the distributions of the training data set of existing and new customers have the same shape at the time of analysis in this proposed online learning environment. So the computational procedure of the test can be considered as follows. Xijt denotes an observation of feature J from the client I at time t. If we let nt be the total number of credit scores, which is equal to the total number of customers at time t, then xj at time t will show the matrix of x and t times kt at time t, with nt rows as the number of clients and kt as the number of features at time t. Loans in banking credit risk literature usually divide into three categories: good for good loans, medium for substandard loans or doubtful loans, and bad for loss loans. The Kruskal-Wallis test is appropriate for this kind of categorical variables with three or more groups, so it is appropriate for our analysis. However, most of the available data sets for credit purpose merge the first and second groups as bad loans, okay? So they want to create a label attribute with two values, for instance, 0 for good loans and 1 for the bad loans. So we denote by S the number of groups in the Kruskal-Wallis statistics, Nijt, the number of observations in group I at time t, and the vector Y with nt rows is the label vector considering, for instance, 3 possible labels for each customer, okay, good, bad, or and substandard or doubtful low, okay? So here we have 3 possible labels. So our IJT is the rank assigned to the jet feature of ith client at time t, and the Kruskal-Wallis statistics would be as shown here with HJT, okay? So then HJT in distribution would have the chi-square distribution with degrees of freedom of 1, okay? So the null hypothesis will be rejected if the computed value of HJT for each J for 1 to KT exceeds the value of chi-square for reselected confidence level and 1 degree of freedom. In credit scoring scenario, we define omega JT to find a balanced measure with less complexity to be followed with 0 as a baseline and negative positive values for making decisions about features. We make omega JT based on the following tau, okay? So first we have to calculate this tau, and then we have the omega as a result of that we can see in this formula. So if omega JT is positive, then the feature is not able to differentiate the classes, and if it is negative, then the feature could be used for the modeling phase to determine the creditworthiness of an applicant. It is clear that this change is only superficial to make it easier to understand programming and represent it as a control chart in a dashboard. And now we study the behavior of omega JT by looking at its distribution function. So now, if we calculate the corresponding cumulative distribution function of the Kruskal-Wallis statistics for any values of y between minus 0.5 and 0.5, the density function of omega JT would be as following, okay, that we shown here. Then we will have this figure as a result. It is clear that the majority of probability density based on the area under the density function curve for statistical significant features is between minus 0.3 and 0. We can expect that most of magnificent fluctuations in the effectiveness of features on our credit score model will happen in a small probability area under the density function between minus 0.3 and 0. Therefore, if we consider only the sign of omega JT in a flag attribute instead of its value to select the informative feature based on positive signs or negative sign, we can manage memory better and eliminate unnecessary features in our computer program with only a Boolean type attribute. That this Boolean type attribute needs 1 byte of memory, the smallest units addressable with the CPU in compare with, for instance, decimal, which needs 12 bytes. It means less memory will be occupied and data transfer in the network will be optimized, right? So especially for massive non-traditional data set with numerous features, it is important. Okay, in this step, we use omega JT in our credit score model to boost the effective features it was shown that omega j-t signs can be a part of credit scoring as an indicator for selecting the features, okay? And now we define a transformed omega j-t to be used as a transformation weight for the kth feature to improve the performance of classification and credit scoring. So let's define WJT, okay, which is the transformation weight of feature J at time t. And we have also the phi as the impact factor of feature K at time t. So we have it as the phi jt. And as we discussed, for a 95% confidence level, if the Kruskal-Wallis test be greater than the amount of the chi-square with the specific confidence that we have, then we reject the null hypothesis, right? It means that the feature contains discriminative information to detect default possibly in loan requests. Furthermore, as shown in the last figure, important fluctuations in the effectiveness of features in credit scoring happens when omega is between minus 0.3 and 0. Okay, now the equivalent values of omega j-t and wj-t to values of h is shown in this table. So this table shows that WJT and phi react impressively to the change of omega in this interval, as we can see in the table. So W close to 1 shows the high capability of the feature to recognize the credit level of the customer. A trend towards 0 means the probability of the feature's influence is decreasing. And monitoring the trend of W for different t and different time could show the level of the model's reliability during the time. If it decreases to 0 randomly and sequentially, then it can be concluded that the reliability of the trained model based on those features is decreasing, and it is a warning sign. Yeah. So we have a warning sign to renew the model by using new set of features. It helps to identify for how long our scoring model keeps up with the initial performance, and it can discover the right time of redoing the training step with a new set of features. It would also be useful to monitor W by considering 0 for excluding the feature from the credit scoring model. So we have a criteria to exclude some features at the specific time, at the right time. And also to the above mentioned advantages, we use W at time t as the power of attribute J to improve the accuracy of the model and to decrease the false negative rate. So for this purpose, we consider all attributes for defaulted customers within the training data set to the power of corresponding W in the training stage. The useful attributes with the higher Kruskal-Wallis test will have W closer to 1. It means these optimal features will experience less change than features with a lower ability to determine the loan default. So in the training stage, we can distinguish between attributes of good and bad loans based on the power of contribution in the model. In fact, we are saving the high performance attributes and we use the less important attributes as labels for bad loans by using the features with high W for making the model and the features with low W to differentiate between good and bad loans. The model's performance is expected to improve. Now, we introduce our new credit risk in the CRI for attributes with interval or ratio scales of the ith client at time t by using the geometric mean that we can see here in this slide. So where here we have the x bar at time t, that is the standard profile of attribute J extracted from the data of good clients. So we calculated only based on the good clients. That's the important point. And if we investigate these credit score characteristics by using the most desirable axioms of the approach to the index number theory, it satisfied most of them. So it would be considered as a good index based on the theories that we have in defining an index. So this credit index formalized homogeneous symmetric average can be calculated as an accurate aggregate measure. And it is able to renew features dynamically and weight out by phi as their impact factors. So the pseudocode of the proposed methodology is listed here. In the training stage, obviously, we will have a very large area under the AUC curve because the values of bad loans in the training set have experienced the shift based on W. However, in the test stage, we are using an independent out-of-sample data set, and we actually have no idea which loan is default. And we show here the first, we apply blindly the transformation for the attributes of all clients in the test data set, including good and bad loans. This will shift the attributes of good loans to bad loans and potentially could decrease the true positive rate, but it will also decrease the false negative rate. Okay, so it is decreasing dynamically. It could be interesting for loan providers, especially when they want to offer a loan to clients without any credit history and only based on big data analysis. In this case, it is beneficial if we can detect the separate sections of good and bad customers and struggle to detect good customers from the moody intersection of good and bad loans in the data set. So there is high similarity in attributes of different categories in this part, and using the CRI as an aggregate of feature of the different features with an interval ratio scale will significantly decrease the required computation for modeling. So here first we input the attributes and the status variable, and the output would be the CRI and weighted attributes. And also we don't change the outliers because some of the outliers have the important information inside, so we have to save them. And for each attribute, we calculate the Kruskal-Wallis test, and then we calculate the W, and based on that, we would have the phi and CRI. And finally, we have the output with the weight attributes and CRI. So now we illustrate the use of our online credit scoring method using two public loan data sets, one German credit data, which is a small data set with 6,377 observations, and another lending club loan data set with more than 2 million observations. And it would be suitable to compare the performance of this credit scoring methodology in different situations, the small data set and for the big data set. So without loss of generality, we assume for simplicity that equal that t at the time would be 1, and we compute the omega and the w at time 1. Only consider it for one time, but by the data that they are in online system, we can put the different times here and do the calculations for every part of the time. So in this paper, we use receiver operation curves, the ROC, to show the statistical performance of the models. And in the ROC chart, the horizontal axis, as we know, represent the specificity, and the vertical axis shows the sensitivity. So first, we obtained the data from German credit data and removed unnecessary features from it. And we continue with the small data. So the results are organized in two parts, starting with the Kruskal-Wallis statistics, W and phi calculation to establish the artificial neural network model based on proposed methodology. Subsequently, the results are detailed, first in terms of model comparison, and then in terms of computation performance. So the phi gives positive values to statistical significant features based on their detection power of default, and gives other zero value, which means excluding those features from the model, right? So the phi based on W is shown here in this table. In this data set, all features are statistical significant, unfortunately. So if they were not, they will be excluded automatically by the formula. So from table 4, the Kruskal-Wallis test for credit risk index CRI resulted in a p-value of less than 0.001, which means that CRI is significantly able to differentiate the categories of good and default loans. So first, we use logistic regression, which is a simple classifier and performs very well for credit scoring as a benchmark. It can produce probabilistic estimation of the binary response variable, and it is a prevalent method for credit scoring. So model A1 in this table, table 5, shows the results of logistic regression for the original variables, and also the artificial neural network for the original variables is represented by A2 in this table. And we use these two models to estimate the improvement of predictive accuracy and the performance of the classification of proposed models. And therefore, the model A3 is built with the weighted explanatory variables, as well as model A4 with a combination of CRI and nominal variables. So we propose CRI in model A4 as a candidate for representing variables with a ratio scale, that is the reduction in the features dimension, and efficient computation resource management. So model A3 and A4 show the main effects of each transformation on variables in accuracy and computation efficiency of the proposed credit scoring algorithm. And model A1 and A2 combine unchanged variables to categorize loans into groups of default and non-default to show how much the new models are able to improve the accuracy and performance of classification. As is common practice in credit scoring, statistical model performance is measured by the area under the receiver operating curve, as we said, AUC, and it is representing in the tables 5 and table 6. So in table 6, the model A3 includes all variables belonging to bad loans to the power of W, except for the nominal features. We consider all nominal variables and CRI model A4 as features of the model. And as is evident in table 6, model A4 did not provide more significant results than model A3, except for less computation. But it is also important. It could be important to deal with non-traditional data sets such as mobile data and big data sources of credit scoring. In this credit scoring case, error rates are not the appropriate criteria to evaluate the performance of the credit score model because most clients are classified into credible customers, 93% here. So from table 9 and 10, it is clear that there is not a significant difference in the performance of the same model. However, by considering the area under the curve as an essential factor of credit risk cost, models A1 and A2 perform the worst, which models including the proposed methodology, models A3 and A4 perform the best. Not only in accuracy, but also in computational efficiency. So to offer a loan based on non-traditional data analysis, the benefit of correctly identifying a defaulter plays a prominent role. And it is interesting to see that having only CRI and the pre-calculation of weighted features on the bad loan section allows discriminative, potentially better clients. So it shows the performance very well here. And by using the area ratio in the test data, the classification result shows almost the same performance of models A3 and A4. So model A4 yields a better performance in computation time. That is critical factor in the performance of parallel and distributed computing for non-traditional data set, and it's very important for applying the method for the big data. So here in slide 28, we use lending club loan data contains complete loan data for all loans through 2007 to 2018. Each loan includes applicant information provided by the applicant as well as the current loan status, current, late, fully paid, and so on and so forth, and latest payment information. So we found two versions of this data set. One contains loan issued through the 2007 to 2015, and another version through 2012 to 2018. As a result, we combined these two data sets and removed the duplicates to obtain a complete data set from 2007 to 2018 with maximum possible cases, okay? So we created two new measures also to be considered in credit scoring models for lengths of credit in years. Credit lengths in years is computed by subtracting the issue year from the earliest year. The issue year is extracted from the issue date, and the earliest year is also substring of the date that the borrower's earliest reported credit line was opened. And also, we want to know the fraction of the initial loan amount that has been reimbursed, and to evaluate the loan provider profit and loss according to model results. So we created a new column named remain by subtracting loan payments from the total loan amount. This will represent the amount of money earned or lost per loan and the outstanding loan balance. So with the data set futurized, credit scoring models are built using binary classifiers with a k-fold cross-validation. So we apply the k-fold cross-validation on a data set with more than 1 million observations, and it contains more than 200,000 default loans and close to 800,000 of good loans. So the method of leave one out cross-validation was used, as I explained. And the purpose was to examine the between sample variation of default prediction. The available data are divided into 10 disjoint subsets, and the models are trained on 9 of these subsets, and the model's selection criterion evaluated on the unused subsets. Okay, so this procedure is then repeated for all combinations of subsets by Python API of Apache Spark, as is represented in the paper, in the appendix. So leave one out cross-validation helps the algorithm to use all data as both train and validation, and consider the mean of the model selection criterion computed over the unused subset in each fold for better accuracy estimation. And also the logistic regression works well for many business applications, which often have simple decision boundary. And also because of its simplicity, it is less prone to overfitting than flexible methods such as decision trees. Further, as we will show in the next slide, variables that contributes to overfitting might be eliminating using lasso or ridge regularization without out of sample accuracy, okay, without compromising out of sample accuracy. So in this case, the ridge method presented better performance than lasso, and we use the ridge. So the following logistic regression are based on ridge penalty with elastic net regularization 0 and reg parameter 0.3 as the best hyperparameters that we found. So to the logistic regression classifier as an industry standard for building credit scoring models, other binary classifiers such as random forest and linear support vector machines are used also for the empirical analysis, and they are more complex and powerful than logistic regression in an application. The interpretability of these models could not be guaranteed, as well as logistic regression outputs. So there are some cons and pros. So the result of the Kruskal-Wallis statistic is here in this table. And based on the purpose methodology and the CRI, the measure that we built, the CRI, we calculated here and check the performance as we can see in this figure, the figure 4. And here we can see all numeric attributes have the Kruskal-Wallis statistic greater than the amount of the chi-square, and they are statistically significant. So we consider all of them for the next step. Otherwise, the program specifies the power of 0 for insignificant attributes. That is not the case here, but if it was, they will be removed. They would be removed automatically. So we start with the default flag rows of the training set and calculate the new numerical attribute, K with powering to W. For non-default loans, we consider the same value in the original attribute for the new one and impute the missing values with the average. For computing the CRI, we have to impute the 0 values in each numeric attribute with average to avoid null result when multiplying by the CRI. By using the average, we nullify the effect of those specific 0 values and extract the information of the other attributes in the benefit of the CRI. And also we discussed in the paper that we need to hold out an unseen portion of the data set to apply blindly the transformation to all attributes of all clients, including good and bad loans, and use it as the main part of our proposed algorithm. The model will apply this transformation for every new customer after deploying, okay? And as we do not have the label for this test data set, therefore we apply the mention transformation to all attributes and create the new features. So the test data set featurized obtained more than 200,000 observations, and the transformation would apply it for all attributes in the test data set. So from figure 4, it is clear that CRI shows an appropriate fair performance to differentiate the categories of good and bad loans, and it could be considered as a candidate to contribute to the modeling phase for improving the accuracy. So we start with the logistic regression with the reach penalty on the original data set as a benchmark. The model B1 in table 8 represent the results of logistic regression for the original variables to investigate the possible improvements in the performance of the classification of proposed models. It is shown in the same table, okay, B2 and B3. The runtime of all 3 models are very close and around 6.6 minutes by PySpark. This data set is representing a very high risk scenario with a high false negative rate. This situation is riskier in comparison with the case of the small data set in the previous section. So the amount of loss shows the benefit of correctly identifying the faulter by the proposed algorithm, and the model with weighted attributes and CRI allows discriminating the bad loans and minimizing the loss. The logistic regression model with new features could migrate the delinquent customers to the reject area and reduce the loan delinquency rate and subsequently the loss amount. So as a trade-off between model sensitivity and specificity, AUC shows almost the same performance among the various scenarios. So our new logistic regression obtained a high sensitivity, around 92%, in comparison with the normal model with a sensitivity of 73%. So overall, the model B1 performs the worst, of which B2 and B3, including phi and CRI features, perform best. So for the second algorithm, we use random forest classifier as an ensemble method. We consider 3, 5, and 10 decision trees to construct each forest and jointly decide upon the created score. The model B4 in table 9 represent the result of random forest classifier for the original variables to investigate the possible improvements in the performance of the classification of proposed models, shown in the same table by B5 and B6. The runtime of all three models are very close and around 30 minutes by PySpark. The table 9 demonstrates that this is a significant difference in the performance of the three scenarios. The normal random forest model is not able to predict any unseen sample from samples it has seen during training, and it was not able to model the distribution of lone situations, as we can see here. But the models BS6, which is a random forest classifier with a combination of 5 features and CRI, perform significantly better. This shows the usefulness of the new algorithm to improve the performance of the models. And also it successfully maximized the profit and minimized the operational costs and risk as another benefit of this new approach by focusing on correctly identifying a defaulter. So the linear support vector machine, SVM algorithm, is considered as another sophisticated supervised machine learning technique with expected high accuracy than logistic regression. As our data set is large, SVM has high training time, more than 1 hour, compared to other algorithms. The results are very similar to the random forest, but the amount of loss is dramatically higher than the two last techniques, regardless of improvement in the performance of the model with the help of our proposed algorithm. The amount of loss is not improved as much as other classifiers. Finally, table 11 represents the best model of each classifier. And again, the new logistic regression B3 produces the best performing model. It has also high interpretability and has been applying for credit scoring as an industry standard for many years. The model B3 has the highest profit, followed by model B6 and B8. It is interesting to see that having new features in all of these models produce decent profits, whereas the normal models of the same algorithm do not, at least not when compared to the proposed algorithm. So the advantage of this approach could be summarized as we say that it occupies less memory and transferring optimized data in the network as a flag attribute, and having a warning sign to renew the model by a new set of features based on the values and trend of W, and improving the performance of the model and decreasing of the false negative rate was another benefit of this approach. And using the CRI as a complementary feature with an internal ratio scale could help the model to identify the bad customers better.